maintainer of the vLLM project. So today I'll briefly introduce vLLM to you, which brings easy, fast, and cheap LLM inference to everyone. And let's be quick. So obviously we are in the era of LLMs, and we are talking about LLMs every day, like search and the chat and coding. So with no doubt that serving LLMs is very slow and expensive. So before LLMs, every single GPU like A100 managed to serve a moderate sized LLM with only 1 request per second. So that's very expensive. And even like Microsoft needs to buy lots of GPUs, and it complains that it does not have enough GPUs. So due to the auto-regressive nature of the large language models, we know the key optimization is to optimize the memory usage of intermediate activations. So we need to cache the KV cache and reuse it. And to enable the flexible reuse of the KV cache, we'll first introduce the page attention technique, which stores and organizes the KV cache into blocks. And this approach significantly improves the GPU memory utilization. And at that time, compared with the implementation from Hugging Face and TGI, vLLM achieved over a tenfold speed up. And even compared with the TGI, it has 2 to 3 times faster. So in June 2023, the vLLM project was open source and received tremendous attention from the community. Now it has over 40, actually this is 48, but I just checked, it's 49,000 GitHub stars now. And during my visit to UC Berkeley, I joined this development of the project, and now it has been more than 1 year since I became involved. So the goal of the vLLM project is to provide the fastest and easiest to use open source LLM inference and serving engine to everyone. And let's briefly visit the usage. So first is a pretty simple and nice end user API called the offline inference, which has the LLM class. So this is for offline batched inference. You can create an LLM object and then just call the generate method, just like you call a normal function. And then it will return all the results of the full batch. And then you can also start vLLM as an OpenAI compatible API server with a single command. Then you can run the normal OpenAI client, or you can reuse it for your own chat service. And vLLM also supports a wide range of models, not only text generation models like Llama and DeepSeek, but also multimodality models like Lava, and also embedding models and real-world models and more, covering the mainstream types of models you would use. And vLLM is the official launching partner of many major LLM companies. Before their models are officially released, they often collaborate with us for better compatibility and integration. So as a result, by using vLLM, you can always deploy and run inference at the very moment the model is launched. And some models are contributed by the model vendors, so you can trust the implementation. And vLLM supports a wide range of hardware, from GPU and TPU to CPU and specialized accelerators. And most platforms like NVIDIA, AMD, Intel, and AWS, Google, they are supported natively. And we are also exploring the plugin-based integration, starting with the Huawei Ascend and IBM Spire. I think this is an exciting direction to build the ecosystem together with hardware vendors. So these plugin-based accelerators, they offer the same user experience as the native supported hardware, while the hardware team can have much better control over the project. And vLLM is highlighted in Google Cloud, like TPU, and also in NVIDIA's GTC launch. And vLLM is already in our daily life. So when you open the Amazon and chat with the chatbot Rufus, you are actually chatting with vLLM. On the Prime Day last year, Amazon actually served 3 million tokens per minute using over 80,000 training and inferential chips. And we'd like to thank PyTorch for the support. This is a PyTorch Day China conference. And the diverse hardware support could not be possible without the support of PyTorch's narrow waist structure. So these hardware platforms, they usually work with PyTorch first, and then they adapt to vLLM. And as model becomes larger, multi-GPUs or even multi-GPUs with multi-machines are needed to run a single model. And these are the scenarios where the problems are prone to occur. And we provide some simple and easy to understand debugging manual for you to understand like where is the problem, how to identify the problem, like is it a hardware problem or network problem or software problem, so that you can identify the issue quickly. And we support a wider range of parallelism. Like we have good support for tensor parallel, which can partition the weights and KV cache. It can also reduce the serving latency if you have good interconnect like GPU NVLink. We also have support for pipeline parallel, which distribute the layers to different GPUs and pipeline the execution. It helps the throughput, but increases the latency too, because it needs, although it needs less communication, but the latency will be increased. And as mixture of expert models are becoming more and more popular, we also support the expert parallel case, which places a subset of experts on different GPUs. During the runtime, tokens need to be routed, dispatched, and combined. And the benefit is that every instance only loads part of the model, so you can have more space for the KV cache. And for large-scale deployment, we are also actively investigating the prefill decode disaggregation. It allows us to separate the concern on the time to the first token and time per output token. And it also enables lots of optimization because prefill and decode, they have very different computation characteristics, so you can optimize them separately. And there's lots of inference optimizations in vLLM. For example, vLLM pioneers the hash-based automatic prefix caching, which accelerates the request with common prefix like the long system prompts. vLLM also supports spectral decoding, which is an idea of using smaller model to generate a draft and then verify them together. And there's also a growing interest to use the one additional layer to propose new tokens like Eagle series or MTP from DeepSeek, which are both supported in vLLM. And as hardware supports more and more native quantization instructions, more and more models, they are trained in a quantized way natively. So LLM can be quantized along 3 dimensions, like the weights, KV cache, and activations. The weight quantization mostly gives savings on the storage, and KV cache quantization can help the attention computation and also enable the larger KV cache. And activation quantization accelerates the matrix multiplication so that you can have faster computation. And I think vLLM has an ecosystem project named LLM compressor. So this project can produce the quantized model, and then vLLM can run the quantized model. And you can check the documentation for the latest support status. I think vLLM has the widest support for the quantized methods. And vLLM is keeping evolving, and it has successfully pushed forward the V1 major architecture update, boosting the performance twice or even further for commonly used models. You can check the announcement blog for more details. And one bitter lesson we learned while migrating to the V1 architecture is about the CPU overheads. Because to fully utilize the GPU, we need to pay close attention to everything happening in the CPU. This is due to the architecture of the accelerated computation nowadays, because we need to use programming language like Python and C++ to control the CPU, and this CPU launches the kernel to the accelerators. So if the CPU does not launch kernels fast enough, then the accelerators are waiting for the CPU to launch kernels, which wastes the GPU time. So what's happening in the CPU? This is an example analysis in the old version of vLLM, which shows that the API server actually takes 33% of the total time, and then there's additional 29% of time spending on prepare input and processing the output. And only 38% of the time is spent on the actual model execution. This is definitely not good. So to reduce the CPU overhead, we propose to optimize all the engine loop and the API server. So here, pre-processing is kind of like you convert the JPEG images into input tensors, and also tokenization. And post-processing means you need to detokenize output token IDs into token streams and do lots of checkings. And then HTTP request handling is like you need to stream outputs to many users. So to reduce the CPU overhead, we use the multiprocessing approach in Python, separating different components into different processes so that they can run in parallel. And then the model itself can run in a busy loop. And for the input preparation part, we take the persistent batch inspired by the LLM deploy. Instead of recreating the batch from scratch every step, input tensors are cached and we only apply the diff because we assume that every decoding step, there's only a minimal change to some requests. And we want not only focus on the performance, but also on the code simplicity. For example, CUDA graph is a powerful tool for accelerating the model inference. But in v0, we capture the one single CUDA graph for the whole model. This leads to increased development burden. And because not no CPU operations are allowed during the model forward. And in the v1 approach, we take an alternative approach by splitting the CUDA graph into pieces using torch compile as a compiler. And we run the attention operation in eager mode and only run like other operations in graph mode. So this makes the max freedom for the attention operation while running other operations efficiently. I think this approach does have limitation, like if your model is very, very small, then CPU overhead actually matters here. Our measurement is like is negligible for 8B models on H100. Of course, if you have smaller models, then this matters. So we are actively investigating how to turn on the full CUDA graph for the full model. But this does need some attention backend modification. Like currently, I think only Flash Attention 3 supports it. And besides performance, we also pay close attention to the user experience. So we provide both PIV packages and Docker images and also 90 build versions for the latest vLLM. And comparing vLLM requires a lot of resources, we know. So we provide some pre-compiled wheels so that you can only add one environment variable, and then you can download the pre-built wheels so that you don't need to compile all the things, because we assume that most developers only touch the Python code. And we also have a powerful continuous integration system, and every code change needs to go through lots of changes. Of course, the cost is that we spend more than $30,000 per month on testing. But given the popularity and the widespread usage of vLLM, we think the cost is worthwhile. And now vLLM is a project owned and driven by the community. And as PyTorch expands to the umbrella foundation, vLLM also joins the PyTorch Foundation as a hosted project. And we also host meetups every 2 months and office hours every 2 weeks. And vLLM is used in many places, including like open source projects and foundation model labs and private deployment and also cloud service providers. So vLLM has been the default LLM serving engine on many cloud services, and you can find many vLLM-based products. And also DeepSeek also publicly acknowledges that its inference engine is based on vLLM. So vLLM is a popular choice if you want to run LLM inference. And vLLM has more than 1,000 contributors now, with several dozens of dedicated full-time developers. They mainly come from UC Berkeley and also big companies who actively use vLLM, like IBM, Red Hat, and Meta, and Google. So we are very grateful for the large community supporting the development of vLLM. vLLM is not only a standalone project, but is also building the ecosystem for LLM inference. So we have close collaboration with PyTorch, Hugging Face, and OpenRLHF, and ASIN, etc. So you can visit our blog post like blog.vlm.ai for latest update. And we're very grateful for all the sponsors. They sponsor lots of compute for the project's deployment. And just for the brief introduction for the vLLM, we strive to build the fastest and easiest to use LLM inference and serving engine. You can find the relevant resources and links on this slide. And one thing I'd like to mention is like vLLM evolves very, very quickly, and there are many new features every week. So even the developers might not have the full landscape of what's the current status. So we actually investigate how to enable AI to help the developers and help the community. So in our documentation, you can find there's an Ask AI button. You can ask questions like what's the current state of the feature support, and it can gather all the discussions from PR link issues and documentations to give you the most up-to-date answer. So that it can help the community grow better without introducing the additional burden for the developers. And yeah, I think that's pretty much it. Yeah, and thanks for joining the PyTorch conference and listening to the WLM talk. Thank you.